So a statement we want to make before we start today. So I think everybody is aware of the news at the moment, and to that I also we want to say a few words. So the current situation in the US worries us all and makes us all very sad, and racism is still a problem in very many countries, and therefore we find it important to make a stand that racism and discrimination is something which has no place in our community. We support and advocate the Black Lives Matter movement. Tolerance and charity are values which we hold dear. So please support your Black community, and there are some things you can do, like donate, support Black business owners, and most importantly, don't be silent. Be an outspoken ally. Talk to your friends and family about racism, call out racism, and block racists from your life. And think critically about the people you directly and indirectly support through your decisions. And to commemorate the deaths of George Floyd and all other victims of racism and police brutality, we want now to do like a few moments of silence. Thank you.
Thanks a lot. Can everybody see me? See my screen? Hello?
I can see your screen.
Okay, great, cool. Yes, so my name is Roi Barkan. I'm from Israel. Nice to electronically meet everybody. Today I will talk about STD variants. It's part of the STL library for a few years now, and it's been boosted a little before. And I will give you a short introduction about it to quickly give you a sense of what it is, and then I'll go deeper into a few, I guess, tricks or variations that I use, which I think can maybe be helpful or interesting for you as well. Okay, so and basically the things mostly relate to the connections between the variant and C unions. The way I try to see how I used to use unions in SQL and other objects and legacy projects, and how we can maybe mix those applications with the STD variant. So that's basically the agenda for today. Let's dive in. I can also say that as was mentioned, I will probably not be able to look at the chat room all the time, but feel free to stop me and ask questions whenever you like. Okay, great. So, first of all, a little bit of an introduction. What is a variant? So CVP reference says that the variant is a type-safe union. Okay, hopefully many of us or most of us remember what a union is from C and later from C++. Bootleg the variant for a long time. Also says it's a safe, generic, stack-based, discriminated union container. Okay, it's a long thing. Basically, the idea that I guess a variant is a union which also knows what type it holds. Okay, so a union can hold many types, but you have to know which type it holds in order to access it safely. And a variant knows the type, which is basically why we call it safe, okay, or type safe. The notion of stack basically means that no replication is needed. The union is sitting on the stack, and discriminate basically means that it's one many types similarly to a union. And we can look at the code that typical variant use it as a variant template with the different types. Maybe so as I mentioned, a typical union you see it looks like a struct declaration, but actually different types you need to choose from them, and the function that uses them, like foo here, needs to access members and it knows which type to use. Whereas in STD variant, its declaration is like a very template. The function can use std get to access members, and std get by default, if you access the wrong type, you'll actually get an exception thrown. Okay, so that's it. In terms of memory layout, just to remind us all, so C struct in C++ struct holds all of its members one after the other. Okay, so a struct of an int, a char, and a double will hold all the members one after each other, and there are also alignment requirements, which means that there's sometimes padding or holes inside the struct. STD tuple is very, very similar. It's not mandatory to have the same layout, but typically it has a very similar layout. And the union will just hold the size of the largest of all of its elements, and similarly for variant. But variant also has to have extra memory to keep the tag and to know what type is currently active inside the union. Typical STL implementations hold the tag at the end of the region, but it's not a must. And as we can see, the tag usually can be small, like one character or two characters, but again, padding usually increases its size. So that's how these things look in memory. And if we try to look online or in YouTube for ways or how people use variants or what people use it for, there are many, many interesting use cases. I try to write down a few bullets of things that I can find online, and I'll show a few of those slides of interesting lectures that you can look up later if you like, of the various uses. Okay, so state machine, basically, we might remember from a university, is potentially just a class or an object that can have one of many different states and can switch or traverse between the states. As it seems, the union or variant lends itself very well to this concept, because, as mentioned, just one of the types is active at any time, and there are various lectures on that. Another common use case for variants is to do dynamic types which have value semantics. Dynamic types in C++ that use pointers or references don't have value semantics, can be copied or moved or accessed similar to typical values. And there are ways where variants' ability to be stack-based and copyable is very, very easy. And the command design pattern typically uses it well. And I'll show an example later on. Another common use case of variant can be very, I guess, trivial way of just using either a single type or nothing, which is optional, or either a single type or a failure, which can be called expected. And there are optional, is entered the STL. There are voices to move expected or something similar to it, also to the library and to the language. So if you're interested in that, you look up talks about that. Another topic is time dispatch polymorphism. People see that a variant is a way to have one of various types which in some ways similar to virtual function calls. And people try to compare and contrast between virtual function calls, variants, as well as the other types or other concepts such as, I guess, type erasure, etc. So people many times refer to variants as well. And the pattern matching is another common, I guess, theme around talks that describe variants. So as I mentioned, state machine, here's a slide from talks meet CPP Germany from 2018, when Nikolai basically gave a short talk about variants. And one of the main examples was a state machine. You can see various states, and variant was used to vary them. You can look at that at YouTube if you like. Again, in 2018, in the US, Mateus also talked about variants and dynamic polymorphism and has a good had a good example with state machines and different events, and showed how to do the transition tables, etc. In terms of commands, here's an older talk from 2016 where David Sankel showed how a variant can basically describe a set of different commands. And again, the value semantics can be very easily used to pass a command around from one object to another, from one thread to another. Commands can be put in queues without a lot of consideration to different pointer, reference, memory semantics, because of the simplicity of variant memory layout. Okay, and moving on, Andrei Alexandrescu in 2018 talked about expected. As I mentioned, this has been later, I guess, talked more and more about, and is now perhaps people will turn it into something of the language. And Alexandrescu said that the ideas and the basics around it had to do with variant as well. Nevin Lieber, who is part of the standardization process of variant, has also talked about optional as a precursor to variant that is basically a refinement of it. And moving on to later times, 2019 and 2020, you can see that Inbal from Israel has talked in CVP-Con about ways to use STD variant and STD visit as an alternative to virtual calls and runtime dispatch. She gave a good lecture on that. And recently, Klaus also described the variant and other methods for doing runtime dispatch in his talk from the London users group. And I think perhaps talked about it in other places as well. Let's move to pattern matching. So pattern matching is basically a way to, or a suggestion to maybe add some abilities to the language to basically try and make a visit more and more powerful and more complex. You can see here Michael Park, who is one of the leaders of this proposal, who says that basically we can use a visit function to access a variant of various types, and the different values in the lambdas can basically help the compiler choose the correct code to run based on the type of the variant. And it's compiler choice, but it's done in runtime. And basically, Michael Park suggests to actually add more capabilities around that, and also actually enhance the C++ language to allow a better usage of this type of technique. It basically says that STD visit is everything wrong with modern C++. It's obviously not exactly his thought, and not exactly my thought. The idea is that variant is a good thing, and can many times be used for good, but STD visit can be cumbersome to read, cumbersome to look at and understand, and that's why he's advocating other ways to enhance the language and use variants, but without STD visit, perhaps. And also, Nevin Lieber mentioned this problem or this issue, and he's quoting even Bjarne Stroustrup saying that he believes that pattern matching should be added as a language feature, and perhaps make a visitation and make the whole act of using variants simpler than the STD visit. So that's a little bit of a short, I guess, overview of what variant is and how people use it, and hopefully you can use these slides and screenshots to look up other lectures of these common topics. So I won't talk about them. I'll focus on variants versus unions and ways that people used to use unions when they did C coding, and how we can maybe help modernize union-based code towards variants. Okay. So basically, the safety of STD variant comes from the fact that it has its own tag that is stored outside of the member, and it's private. Okay, the fact that it's a private member means that no one can change it under the hood. Only the constructor and assignment operator can change the tag. A user can't mistakenly put one type of object in the variant or in the union of the variant and access it as a different type. The compiler itself knows all the possible alternatives, and this gives a lot of safety, which cannot happen in typical C union. Okay, here we can see an example of C code that we used to write perhaps in the past. We have a union of 3 different types, and this type of example I'll try to, I guess, enhance it as we go along this the rest of the lecture. And I'll say that that you can see a function, a C function, which is called setID, can receive this union of identity card. It also needs to accept another argument of the type, and can, if you like, it can switch on the type to know how to access the different members in the union. As you can see here, this C code is not very safe. And if you like, I can maybe stop for like 10 or 15 seconds, so you can try to see if you can find, I think, 3 different bugs that I entered into this C code. Okay, so I'll stop for like 10 seconds. Okay, so basically, I don't know if you have ideas about the bugs. Can you hear me, by the way, still?
Yes, we can hear you.
Okay, cool. So one of the bugs that we can see here, right at the last line here, is an access to an incorrect member. We can see that in the case of a citizen, we still mistakenly go to the passport member, which is a bug and a mistake that the C compiler will not catch us doing. Another is we might forget missing types. Okay, here the union has 3 types. The union has 3 types. The switch statement only has 2 cases, which is a mistake. And obviously, some compilers will warn us about that, but the C standard doesn't say anything, and even the C++ standard doesn't say anything about this code. This is totally legal. And the third issue here is that is the infamous break statement inside the switch, where most people that use most case statements in switches, they actually need to break at the end of each case. But the standard doesn't default to it. And again, sometimes a compiler can help us, or some static analyzer can help with that, but it's not very simple, and the standard doesn't say anything about it. And if we use the STD variant, all of these issues are solved much easily. In this case, I'll have, as you can see, a variant of 3 different types, and I can give each type even a method called check, and the STD visit function can be used to create the correct call on each and every type very safely. And in case of any problem or issue, the compiler will catch us and will let us know that we did things incorrectly. Okay, I should note that if one of the types didn't have a check member, then a compiler will give us a compiler error, and everything is very safe. Okay, again, so that's the basic idea of the safety. But I have to tell you that this is sort of a straw man. This example on the left is an example that has many bugs, but this is the way that it's legal in C, but actual programmers that write in C, or even programmers that use unions in C++, don't do it this way. They usually write safer code and have various idioms and various ways to write things more safely. And let's look at that a little bit more. And
so Roy,
yeah,
there was a question from, who was it? Somebody has a question, had a question for Eduardo. Was that you? Maybe.
Okay, so.
Okay.
Okay, are we good?
Yes, we are good.
Okay, cool. Great. So usually what people do in C, or many times what people do in C when they have a union, is they do put the tag right next to the union, similar to STD variant. Even though they don't have STD variant, they can still do it. And there are typical ways to do it. One way is to have a struct that holds basically two members. One is the type, and the next is the union. I'll call it explicit header, meaning that there are the values and there's the header, and it's explicitly mentioned outside of the different variations. This is a nice alternative. I use it many times. And another way is to put it implicitly inside each, put the header implicitly inside each and every member. We can see here, I took the identity card, and I basically have the two different types, the citizen and the tourist, as well as a header type. And I manually copy and paste the first type element into each and every one of the types. Okay, so this way I know that the first member in the union is the same member. All the time I can access it and know which type I'm using. Okay, one might think which is better, the explicit or the implicit approach. And it definitely seems that the explicit approach is safer, right? Because there's no code duplication. I don't need to write the ID type in each and every place, and everything is much more condensed. However, people still find themselves using the implicit mode, typically because of two things. First, I think mostly is that sometimes I would like to write a function, as either C function or a C++ function that accepts as an argument one of the types, just a citizen or a tourist. And if I have a function that accepts the citizen or the tourist, because I want to be specific just to one of the types, I sometimes do want to access the header and access more fields who might exist in the header, just in order to be to get a better view of how I use things. Okay, so what I see a lot of times in code is this type of preprocessor usage, where I like a define of all the header fields, and then I can have a union of different types, and each of them starts with those same header fields. Okay, and this is sort of like the best of both worlds, meaning in the sense that there's less duplication. I'd say all the fields of the header only exist in one place in the preprocessor macro. And still, if I write a function that only accepts a citizen or only accepts a visitor, that function has access not only to the specific members of the subtype, but also has access to the header fields and can use them. Okay, so that's basically things that people do in C. But in all of these approaches, basically the memory layout is the same. The memory layout is such that the first few fields, or at least the tag, are common across all the union members. And after that, we get the union with different subtypes, I guess, or different variations on the specifics of the union. Okay? And this layout is very, very common, not just in people's code, but also in actual, I guess, streams of data or in actual data structures that we see in the world. Okay, so TCP, IP, and various financial protocols, it's very, very typical to have a packet or a buffer that can have various types, and like a layered approach, the header or the prefix before those various types will have a tag that tells us what the type is. Similar for the various file formats, to work a little bit with the executable L format, and it also has the various words. And before the record or at the start of a record, you have some header that tells us what the type is. Similarly, there are various serialization libraries, especially ones that specialize in binary serialization that are cross-platform, across different platforms and languages, which also use this mechanism in this type of memory layout. So this layout is not only common in C language, it's also very common in the world. And many times, if I want to write C++ code that interacts with other languages or with C, I will want this memory layout to stay the same. But still, I want to maybe not use a union, or maybe see how I can, with this layout, be safer than C, and manage to get some of the good parts of STD variant and be safe. So that's basically the idea. And before I jump to my suggested solution, I want to talk a little bit about the C++ standard, okay? So the C++ standard discusses these types of things and discusses what are legal and illegal or defined and undefined ways to access unions. And basically, we talked about STD variant, and we said that STD variant is very, very safe because it never accesses a union without knowing the tag in advance. So STD variant can correctly know which member of a union to access before even accessing it. But actually, the C++ standard is more relaxed and more lenient. In many, many times, it's okay to access the header of a union in a standard way if I know that the header has the exact same members across all the variations, across all alternatives. So basically, standard for a long time, I'm not sure if it's all the way since 1998, but for a long time, the standard, C++ standard had the notion of a standard layout class and a standard layout union. And basically, the C++ standard says that the standard layout classes are useful for communication with code written in other programming languages. So the standard itself understands that there are typical layouts that people are, I think, used to and people rely on when communicating with C, communicating with Python, etc. And the C++ standard actually allows it. It's considered defined behavior. But there are various constraints. If I want a type to work this way, or be the standard layout, it has to meet various constraints. So it cannot have any functions, no RTTI stuff. All the data members have to have the same access control. So everything has to be either public or everything protected or everything private. If it has both private types and protected types, it's considered not a standard layout. All of the non-static members have to be in the same class. So if I have a class hierarchy of base classes and derived classes, etc., it's still okay, but I need all the actual members to sit in the same place, which is actually very cumbersome, but it's one of the rules. And there are several other rules. I won't go about it. But if I manage to stick with this and have a union of all members that are all, I guess, standard layout, then the standard guarantees that I can actually use them even before I know the exact, I guess, the exact type within the union. Okay, and as of C++ 11, there's actually a utility called isStandardLayout that I can use to check whether an object or class is standard layout or not, and I can use insert to make sure that my classes conform with this idea and with this concept. And in C++ 17, like many other type traits and type utilities, we also got isStandardLayout V, which is just a nice syntactic sugaring. And the STL standard basically, or the C++ standard basically says that if I have a standard layout union with an active member of struct T1, okay, one of the members, it is permitted, it is allowed to read one of the data members of another union for T2, if this other member is part of the common initial sequence of T1 and T2. So basically it says if I have a union with two different types, T1 and T2, they can have a common initial sequence. And those common initial sequence, I can access them either as part of T1 or T2, and it's still allowed and legal. And happily in C++20, we also received a new utility, which is called the is corresponding member, which is a const per function, where I can actually go to two different types of a union or two different types of classes and ask the compiler, please tell me at compilation time, hey, are these two different types compatible? Is it legal to access my union, the member called the type in the header, even before I know exactly if it's a citizen or not? So these are basic tools that the standard gave us to use or to access a memory that's in this memory layout that we described above. It's the typical one for accessing C. Okay, so that's basically the idea, and based on that, we can go and start looking at solutions for this problem, or ways to approach this problem. And my first approach is called the intrusive variant. Okay, so intrusive variant is basically a way to access the memory layout of C with extra safety. So if in the old world we had a union of 3 different structs, and all 3 had the first a member of the type, I can use an intrusive variant with a type def similar to STD variant. And basically, I will tell my intrusive variant that all the types are basically, or my tag is of type ID type. Okay, and I will give it also the offset, how many bytes within this union you could find these bytes or this member that can be used as a tag. Okay, and after I tell my intrusive variant how to know the type of each and every member, I can go ahead and list the typical the different members. I can say, okay, this is a variant or intrusive variant of 2 different types, a citizen and a tourist. And we'll tell it, if you see in the tag ID type : citizen, it means that there's a citizen in there. And if you see tourist, it means that there's a tourist in there. Okay, so this is a kind of complicated, I guess, wording, and perhaps there are ways to make it simpler. But this is a way to create a variant with the same memory layout as we can see above, and with basically where we have more control on the exact location, and also the exact values within the tag. Okay, so this way I can use intrusive variant if my header has even more fields, and the tag is not exactly at the start of the structure, but a little bit inside it, and I can declare exactly what I want and where I want it. And alternatively, if you want something that's maybe a little nicer to write, I can put I guess like a type def within each of the members of my union, which gives the exact value of the tag that I wanted. Okay, so I have my type in the citizen, in the tourist, with the exact ID type : value, and that way I can do my tag def of the intrusive variant a little more in a shorthand. I still need to tell it what is the type and what is its offset, and then I can move on and enumerate each and every type and the tag value that corresponds to it. Okay, and basically, once I use this, I can use it very, very similarly to standard STD variant. And the most specifically, I can use a visit function similar to STD visit and still run at constant time complexity. Okay, I can basically the intrusive variant creates its own lookup table. Okay, based on the tag values that the user supplied. So the lookup table can be larger, because if you put values that aren't I guess incremental, the will be larger, but still you have a full control, and you don't need to write your own switch statements yourself. You just call a visit on the intrusive variant, and it will do the lookup table and the switch, I guess, by itself, and be safer. Okay, so that's an intrusive variant. We can see, by the way, that this approach is safe according to the C++ standard, meaning because I created my union this way, these objects are all standard layout, and the ID type in the right offset is a part of the prefix. It's all safe, it's all legal. But the intrusive variant by itself doesn't currently check okay, we'll just go to the offset and do a reinterpret cast to the ID type and hope that everything is good. So it's still not as safe as STD variant, but if you created your type def and your types correctly, you get the safety after creation of the STD visit, like visitation, without needing to write your own switch statements, etc. Okay, and if we go further to C++ 20, where we get these new functionalities around safety, we can do some extra things. I haven't implemented this myself because I don't have a C++20 compiler right now, but I believe this could be done as well. As you can see, I basically write a small function called the declare safe intrusive variant, and this declare safe intrusive variant basically accepts 4 arguments, the different types and their tag location and tag value. Okay, and this helper function basically uses static asserts to make sure that the 2 types, citizen and tourist, are actually standard layout, and that the 2 locations, citizen : type, citizen and tourist : type, are both within the common prefix of the union, and can do that for all the different variations. And that way, this declaration can actually give a compiler error in case I try to give it types that aren't in the same offset or aren't in the same prefix, etc., and get the extra safety even on the declaration side, and less mistakes that you can do that the compiler won't catch. Okay, and I think perhaps I can use some generic lambda tricks to make this sugarcoating even simpler, and allow me just to write a single lambda that accesses the type member and the my type member, but I'm not 100% sure about it. Maybe I can discuss that a little bit more either in the future talks or in the comment section in the meetup. Okay, so this is the intrusive variant. Okay, now in the next slide I'll move to another solution, which is I think nicer, but has a problem, which is not 100% defined behavior in a C++ standard at the moment, which gives even more safety. Okay, so the idea here is that intrusive variant is safe, but still has some boilerplate, and my notion or my understanding is that this division of a header and extra members is very, very similar to base classes. Okay, in C++, many times the base class of 2 different functions is very, very to a header. It means everything in a base class, is actual fields that are actually part of all the different derived classes. And actually, most of the times, most of our compilers will put the layout of the or all the members in the base class actually in the header. Okay, so this is a nice approach. And if I put a base class, I can make various members of it a constant, and that way I get some extra safety in making sure that all of my variations have exactly the same header in the exact same location without any duplication. I will show you the example in my next slide. And this way I can use various utilities in the C++ language, like isBaseOf, etc., to ensure that things are safe. Okay, the only problem is that although it's very, very nice and it works with most compilers that I tried, the C++ standard doesn't really allow it. The C++ standard, if I put a variant of or even a union of 2 different types, which are actually derived from one same base class, and that base class has members, like which are my header, the derived classes have other members, then this by itself is not considered standard layout. Okay, and because it's not considered standard layout, this approach that I will show in my next slide will actually not be a defined behavior in the C++ standard. And I wonder what you think. I personally think that because it's rather useful, and also because it works on many compilers that I chose, it might be worth it to try and maybe update the standard and allow this to be a standard conforming. Okay, so what's the idea? The idea, I call it variant of base. Basically, it says let's put all the header in one struct, and then the different variations we can put it. They can actually use I guess derived mechanisms and the base derived relationships in order to declare all the header within them. Okay, so you can see that both the citizen and the tourist, they derive from ID header. In their constructor, they pass their types to the ID header. The type itself is const. Okay, so the compiler guarantees that basically I can't very easily change the type once it's there. And with this mechanism, I can more easily create a variant of base where I tell the compiler, hey, I want a variant with of many objects that they all derive from ID header. I will give it two small lambda functions, which help it know how to access the header and get the correct information from the header to differentiate the different types and values. Okay, this is sort of like the replacement for a VPTR, or a virtual pointer. Okay, so the first lambda, you can see, is a lambda function that accepts a header and returns the exact member which holds our tag. Okay, and the second lambda is a generic one. Okay, you can see that it receives auto, and it basically, you can see it returns my type. Okay, you see there are various tweaks around here about the decal type, etc. But the idea here is that this lambda, I can give it a pointer to either a citizen or a tourist, and it can tell me at compile time what is the actual tag value for the different types. Okay, and after I put these the type of my header and the two lambdas, I can list the different versions of the variant. And with this thing, I can have, again, something that I can use visit on. I can work with this very similar to how I used to. This actually is the same memory layout that we've talked about before, but in many aspects it is safer because I know that I guess that the class inheritance structure causes me to know that all the members are exactly in place and are exactly in the layout that I want them. Okay, so this is a variant of base, and these are two different approaches that I can give to being a little bit more safer than unions with the same or with the old memory layout of a unions. And I would say that these two approaches are very can be used even in tandem. I can have a C application communicate technically with a C++ application, one of them using unions and the other using those. Okay, so this is basically one complete idea about how to use these layouts in C++. And now I'll move on to a different topic. So if you have questions about this whole memory layout approach and these concepts, I'd be happy to, this is a good time for maybe questions. And if there are none, let's talk about the next use case that I wanted to give you an idea about things to do with, which is arrays of variants. Okay, so again, many times we have variants, but we don't need to use just one. We need to use a stream of many objects, and each of them is a variant. Okay, and as you know, if I use an STL vector of variants, the memory layout will be just one object after another, and the size of this thing can be very large, because in this example I have an array of my first object is of type ID. The second object has a UUID. The last object is also an NID number, and the size of the vector and the size of each member is the size of the largest one of all different variations. Okay? And the fact that this is so large means that it can be wasteful in terms of memory, in case of case utilization, etc. Okay. Similarly, by the way, if I use a vector of Intrusive-Variant that I showed before, it's the exact same thing. The tag moves from one place to another, but still the size of each member is the size of the largest member possible. It's not condensing. It's not the typical way that someone will, I guess, transmit or save into a binary stream, a list of many objects, which is what we used to do in C. Okay, so in this language, or in the real world, the typical way to send a large number of these unions is to send a tag, and after the tag, or put a tag after the tag, only keep the memory layout of the exact correct member that is active. Okay, and right after that, I can put the next tag of the next object and put the robot in it, etc., etc. And as you can see, this C-style approach is much more condensed. I don't have any this wasted bytes. Okay, but it's a little less convenient to work with than a vector, okay? Because with this concept, I cannot. It's not easy to jump from one object to another without knowing the actual tags. Okay, I hope this makes sense. And so in the next slide, I'll try to give a few utilities to work with this type of data structure and this type of condensed array, where we have basically one variant after another, but instead of putting them so far away from each other, the distance, which is the maximal distance or the minimum distance that is allowed, I put them really one after the other in a condensed fashion, similar to the way that we will usually, I guess, transmit them over the network or write them in a binary file. Okay, so basically the idea is called the condensed variant iterator. Okay, and the condensed variant iterator is basically an iterator which is a variant, an iterator over variant objects. Okay, and I can use a visit to visit its members. Okay, but the thing is that its operator plus plus knows exactly to move forward the correct amount to the next member, even though it's condensed. Okay, so with the condensed variant iterator, I can use STL algorithms such as std copy or std find, etc., to go over arrays or data structures or of information without really thinking too much about the memory layout and about how to access this information. And I can use the information condensed in memory. So that's a condensed variant iterator. We can see that it's only a forward iterator. It's not access, and it's not even backwards iterator, because this type of iterator cannot know how many bytes to jump if it doesn't know the header or the tag. Okay. Similarly, if we want not just an iterator over memory, but if you want to an actual data structure, condensed variant queue is something that can be used, which is a queue, a FIFO queue, where you can put things out of the back and pop things out of the front. And it also basically uses only the memory that it needs for each of the variants based on the types that we put in it. Okay. And the root of the logic of both these types of constructs is this visit function that you can see that that visits a pointer to any type of the variant that I have. And what it does a static cast from or it takes the pointer and does +1 and does a static cast of that back to the base or to the header type of all of my variants. And the basic idea here is that this lambda that I put is a generic lambda. Okay, and the auto implementation basically converts to each and every type of those of the variations or of the alternatives in my variant. And that means that if I have a variant with 3 different alternatives, I will actually get 3 different lambda implementations where the p+1 has the correct size of, the correct alignment of the different types that I'm using. Okay, and then when I can static cast it back and have a pointer to the next, which is exactly where I want to continue traversing memory. Okay, so this is my second little tweak or tool that can be used with variants in case you have many of them in RAM and you want them to be put one after the other. You don't want them to be too far apart just because a union or a variant takes the space of the largest of all of them. Okay, so this is a condensed variant. So basically, I try to tell you a little bit about variants and about unions. I try to show you a little bit that how unions are actually used in the real world in C code, and why it's not very easy, I guess, to just take a union as it is and change it to std variant. And I try to give a few pointers or tips or tools on how we can use some of the C++ safety that we see in variants without changing the memory layout, and with being a little more compatible with unions and with memory and objects as we're used to do them before. Okay, so this is a summary that I have. We have, hopefully, if you're not too bored, I'll be happy to answer questions. And I also have a little bit of extra content related to variants, to pointers, and to de-virtualization. So let's stop right now. I'll be happy, Hendrik, others, if you have any questions about what we had so far. I know that I was relatively quick, but hopefully you managed to keep up. I'll be happy to go back to slides. And if you have like 10 more minutes and you want me to talk about this extra content around de-virtualization, I'd be happy to talk about that as well. So I guess this means there are no questions. I hope that people manage to keep up a little bit at least.
Yeah, so I will just ask again, are there any questions? So you can just unmute yourself and ask your question right now, if you have any. So maybe I can ask a question really quick. So let's say you're starting a new C++ project today. Are there any reasons to use a union over a std variant, in your opinion, at the moment, if I start with a new project from scratch and don't have any issues with compatibility to C, for example?
That's a good question. I think my main concern might be related to a binary compatibility, either with C or with some memory or file layout. Okay, so there are cases where I want the tag to be known, or I want it maybe even to be compatible with future versions of my own code. Okay, so in the STD variant, there's no constraint regarding the actual tag values. Okay, and there's no way for me to actually go and memcopy or do anything with my information and access it later on. So that might be the main use case where I would consider taking control of the tags and using a union or an intrusive union myself. But other than that, I think STD variants are great. So most cases, I will just go for STD variant, I think.
Yeah, that's also my opinion. I personally love std variant for the applications in compile time polymorphism, and you have shown also many other cool use cases. So
yeah.
So any other questions from other members of the meeting right now?
Yes, because of your internet connection troubles at the start of the meetup, can you please upload your slides somewhere?
Yes, of course, of course.
Okay.
Yeah, I will put a link to Google Drive on the meetup page and wherever you like.
We can also distribute this link via Twitter or the meetup page.
Happy. I'll be happy to do it. Okay, cool. Yeah, by the way, in this slide here, you can see at the bottom part the logo of Istra Research. That's the company in Israel that I work for. We're doing financial algorithmic trading, high frequency trading. If I don't know if people here are in the finance sector or have a chance to visit Israel, but if you do, you can maybe visit or talk to me about Istra as well. We do a lot of cool things with C++. Okay, so if we have 10 more minutes, I want to talk a little bit about de-virtualization. It's another thing that is sometimes talked about and discussed regarding performance of dynamic dispatch code. And I wanted to show you a nice trick, sort of, that can use STD variants or concept around STD variant to help our compilers with the de-virtualization. Okay, so I'm not sure if you even know the concept too much, but just show you here slides. I think it's from about 10 years ago, maybe even more, where Andrei Alexandrescu, our good performance guru and algorithms guru, have displayed and talked about the cost of or potential cost of virtual access codes, and they also tried to suggest in his talk I think it was called Going Native. He tried to suggest a way or a scheme to do something similar to virtual tables, but without virtual function calls. And in his example, basically, he said that he gave a lot of information, but basically tried to create his own virtual table and use tags similar to tags of variants, but the tags replace actually the virtual pointers, and they're much smaller. They're only 8 bits and not 64 or the size of a pointer. And he said that it's a big win to have these smaller tags. And he's tried to show the way to do it and to hopefully de-virtualize things and help make virtual calls a little cheaper in terms of call. And I want to give you my take on this, and also remind us that the STD variant and STD visit are also types of lookup table things, and we can use them to make these types of, I guess, code optimizations maybe easier or simpler. Okay, so first of all, I talk to you a little bit about why are people so afraid of virtual function? What is the actual cost of virtual functions? And I think that many times when I talk to people about this, they mention something called branch-based prediction. Okay, and branch-based prediction is a microarchitecture type of concept related to the fact that our CPUs are very, very advanced and very, very speculative. And many times when the CPU processes our code, it needs to look ahead and try to understand not just what is the current, I guess, instruction that we are running, but it actually tries to speculatively execute more instructions at a time and do this in parallel. And if we have an if statement or a branch statement or an indirect function call, the CPU needs to predict where the branch is going to go. What is the next piece of code that we want to run? When we think about it, and especially in the 10 years that have passed since Alex Andreescu's talk, there have been a lot of improvements in CPUs, and the processors have pretty good predictors. Meaning that usually, if I have a virtual function call, most of my objects are of the exact same type, and most of my virtual calls are going to the same location. Processors are actually pretty good at predicting it, and even if most of the calls just 50-50, but with a good pattern, there's a good chance that the predictor can learn the pattern as well. I think one of the reasons for that is that the processors themselves, in some manner, have a better understanding of our branches than even the compiler. The reason is that the processors, usually they can see the assembly code, but they also can see the data. They actually do machine learning. They actually learn all of our branches as the code runs. And as they see patterns, they optimize the future branches based on the behavior of their predictors in the past. Our compilers, on the other hand, usually only see the program. We don't see it. We don't let it see the data. Okay, and for that reason, compilers usually, when they have a virtual call, it's much harder for them to try and guess which is the likely path and what is the likely prediction of the code that we want to get to through the virtual call. So there are ways to obviously help the compilers. Typically, two buzzwords that are discussed many times are PGO, which is profile guided optimizations, and LTO, which is link time optimization, sometimes also called whole program optimizations. So PGO basically says, let's give the compiler not just the code, but also some data, some benchmark data, or some profiling information to let it have more ideas about the patterns and the actual targets of most of our virtual function calls. And the LTO tries to help the compiler by letting it know all of the options or all the alternatives of a virtual call. So in my use case here, I'm not using the use case that I'm trying to describe is a use case where I don't really have a variant. I actually have a base class with a virtual method, and through the virtual method, I need to call a virtual function, and the compiler needs to guess which virtual function to call. And sometimes I have information that I know about, and I want to pass it to the compiler. Okay, so in C++20, there's this another notion called the likely. There's a likely attribute that people can put on I guess case statements inside a switch, and also on if statements. But it's not possible in C++20 to put a likely statement on a virtual function call. To say, hey, this is a virtual function call I want to call. I have a pointer to a base class, but I want to tell you that the likely derived class is one specific or two specific classes that I can think of. Okay, and if I tell the compiler, it can give a lot of performance boost, because yes, the processor already has a good predictor, but the compiler itself, unless we we give it this information, it cannot do any good inlining. It cannot do inspection in and outside of the virtual code and rearrange code to get better performance. Okay, so here's the example that I would discuss. As mentioned, I have a base class with a virtual function. I have two derived classes that implement the virtual function. And I have, and basically, my idea is that I know that D1, for example, is much more common than D2 or much more important. Okay, so consider, for example, that D1 is the derived class that I use for production, and D2 is another implementation, like a mock implementation that I use only for testing. Okay, so I want some way to tell the compiler that out of this pointer to base that I have, D1 is much more common. Okay, so look at these two last lines in the slide. Instead of calling p-foo or p-arrow-foo directly, I create a variant of a pointer to base and a pointer to D1. Okay, my variant, its size of is just the size of a pointer. It's just like a pointer in terms of size, and its content are just the same contents of a pointer. It also has the tag, because every variant has a tag. The trick here is that the visit function now has a generic lambda. So the generic lambda will actually be implemented into two different variations. I have the one implementation which is specific to D1, the common case, and another implementation which is for the base class, which does the actual virtual function call. And that way, I'm trying to hint at the compiler, hey, I know that this is a virtual thing and almost everything is possible, but I want to give you a hint that try to look at D1 first, and only if the object is not of type D1, then go and do the virtual function call. Okay. I also want to mention here that in this example, both the D1 object and the D2 object are final objects, okay, meaning that if I know that the type is D1, there's no need to do any actual, I guess, understanding of what's going on here. Okay, so that's the basic idea. I hope it's not too complicated. And here's my first attempt in Compiler Explorer to do this thing. Okay, so you can see I have this this base class with a virtual function foo. I have a common and a rare cases, both final, with two implementations of the function foo. One returns 750, the other returns 222. And my test functions tries to use std visit in this way, and hopefully get some performance boost in the case that the actual variant that I received points to the common case and not to the base case. And I'm not sure if you're experts on assembler, but to give you a brief overview, I can tell you that line 20 in the assembler here on the right side is a virtual function call. Okay, we can see actually it's lines 18, 19, and 20. Okay, you can see that basically trying to line 18 reads the virtual PTR, lines 19 reads from the virtual table reads the pointer to a function, and then line 20 does the virtual function call. Okay, and what you can see to some extent is that on line 11 we have another call, yeah, which is a call to another sort of like a virtual table, which is the virtual table of the variant. Okay, so this approach, as you can see, didn't really improve a lot in terms of performance, because instead of doing one virtual function call, I basically do one call in line 11, and then in some of the cases I drop into line 15 and return 750. That's the common case. And if I don't have a common case, I need to do a second virtual call. Okay, so this is not the performance gain that I expected. And the reason for that is that std visit itself, as we discussed, implements a virtual table and does indirect calls. But here's the catch. And I think in a talk by Klaus Cipilon, he also discussed it a little bit about the difference between the std visit of most client compilers and the implementation of the variant and std visit by Michael Park. He noticed that the visit function can be implemented without a virtual table, or with a virtual table only for very, very rare cases. And here you can see that I implemented the visit no table function myself. This visit no table function doesn't do a virtual table. It basically does a recursive call or an if-else statement on the different indexes here. Okay, I don't know if it's easy to see, but the visit table here basically is templated on the index of the tag that I want to access. If the index that I'm currently implementing, that's currently instantiated, is equal to the index of the variant, then it's the end of the recursion. I can just call my visitor with the exact member that I need. Otherwise, I call visit table recursively, okay, with index +1. Okay, so this implementation is technically much slower in case of a variant with many variations, but but because it converts a switch statement, or it converts a virtual table into many if else's. Okay, the thing is that these many if else's can be, if they're left on their own by themselves, they can have bad performance, but compilers are really good at optimizing them. And look and see the assembler that was generated here. Okay, the assembly here now is much simpler. We can see there's a test for the tag. Okay, if the tag is for the common case, we jump to line 6 and return 750. Okay, or we inlined the foo function. Otherwise, we go and do the virtual function call as before. Okay, so this is basically a nice way to use variants to pointers, and pointers to I guess functions, in order to hint to a compiler what is I guess the common case and what they should optimize for. Okay, hopefully this example of converting this code into 8 lines of assembly code, and where the common case doesn't have any virtual call. There's just and not even call to the common colon foo function. It just goes and calls and returns 750. Should show you the potential ways to use this to really help our compilers make our code faster and simpler. Okay, so this is my bonus content. I hope this was also nice and informative. This is basically the end of my talk. If you have any questions, now's a good time. And if not, thank you very much.